So thank you very much for this invitation. So yeah, I will explain what means this bead process and bead ensembles. So the idea comes from a process introduced by Boutillier. So it's a process on Z times R. So we have countably many lines, and then we have points on these lines, and they interlace. So between two consecutive lines, the points interlace from one line to on the other. The process is translation invariant in distribution in both directions, and the expectation of the number of points in an interval is proportional to the length of the interval. So there is a homogeneity. And the conditional distribution of any point given the other points is uniform on the interval, which is allowed by the interlacing property. So if we have, we know that there is one point, okay, in some area of the lines, then basically, so there is a limited domain because of the interlacing, and you have a uniformity of the distribution, of the conditional distribution.
Do you have a picture?
Yeah, I can draw. We have, these are the lines. You have countably many. And then you have the points here. And then they interlace. So for example, conditionally on the fact that there is of all the points except this one, if we know there is exactly a point here, then it's uniform among in the interval where which is allowed. Okay, there.
The previous properties define the thing?
So it defines. So it does not define completely. So I will come back to more precise things a little after. So here there is. In fact, the process is the bit process is determinantal, and it depends on some parameter. So here I take a positive measurable test function, and I sum on all p-tuples of distinct points. And here I get an integral with some density given by this determinant. So the determinant here gives intuitively the probability to have a point near T1 and a point near T2, a point near TP. It's a joint distribution of the joint probability to have simultaneously a point at T1, TP. And this is given by this determinant. And then I will say what is K gamma. Okay, so this is the intuitive meaning. And the kernel, so there is an explicit formula. And okay, I will not detail the meaning of this formula, but in particular, if we look at the points only on one line, so we take the line 0, for example, and we forget all the other lines, then we get a point process on the line, and the point process on the line is a determinantal sign kernel process, which means that the kernel how do I yeah. Okay, so the kernel restricted to a line is given by this sign T over pi T. So each line is what is called, so the determinantal process.
How can it depend on K being positive or negative when it's translation invariant in Z direction?
Sorry. Sorry, or how can it?
Supposed to be translation invariant.
It's translate. In fact, the kernel. So what happens is the kernel is not symmetric, but when you compute the determinant, it becomes symmetric. So this is yeah, some kind of subtlety. So in fact, so it has been proven by Johansson and Norderstam that the bead process is a microscopic scaling limit of the eigenvalues of consecutive minors of the Gaussian unitary ensemble in the bulk of the spectrum. So we take a matrix, Hermitian matrix, with complex Gaussians, independent complex Gaussians above the diagonal and real Gaussians on the diagonal, and then the matrix is Hermitian. Then if you take consecutive minors, so the minors n and -1 and -2, and so on, and then you zoom again, you zoom around some point of the bulk of the spectrum, then you get some interlacing points, and at the limit you get this bead process. So this is a link with random matrices. The parameter gamma depends on the position of the bulk around which the scaling is centered. And it's natural to expect that the similar scaling limit exists for the Gaussian orthogonal and the Gaussian symplectic ensemble. And in the paper, so in the paper with Balint, I'm presenting, so we construct such a scaling limit. So instead of just the GUE, we consider the GOE and the GSE. And more generally, we have a construction which works for all beta ensembles. So there is this parameter beta, which is 1 for GOE, 2 for GUE, and 4 for GSE. And this can be generalized for all beta. So this is what I will explain later. So in random matrix theory, it's often useful to consider the Stieltjes transform. So we have a measure on the real line, and then we integrate with respect to 1 over lambda minus z. And then we get a function of z. So z, in general, we consider z not real. And also we perform this integral, and we get a function on the complex plane without R. So here in our paper, we take an infinite measure. So instead of taking mu probability measure, for example, we take some infinite measure, and in some situations, we are still able to define the Stieltjes transform. So here I take a set of points, so countably infinite set of points, discrete. And I suppose that so the number of points between 0 and x is does not grow more than linearly. And here, in fact, so what basically the variation of the number of points in different intervals. So if we have intervals of size of order x, then the difference between the number of points in the two intervals is it grows lower than x. So we have somehow in the first order the same number of points in all intervals. So in the interval 0x, so we have some symmetry. In 0x and in -x0, we have at first order the same number of points. The variation it has some lower order of magnitude with this log to the -2. So we have something quite well balanced set of points. And we have a family of positive reals, also quite well balanced. So the sum of the k first positive is proportional to k, and then plus an error which goes slow to infinity, slower than the main term, so slower than linearly. And now we consider an infinite measure. So we put Dirac masses at lambda k, and with weights gamma k, and the lambdas and the gamma satisfying the same condition as before. So informally, mu, because of this homogeneity and this x plus big O of x over log square x, we can say that mu is not too far from the Lebesgue measure in some sense. And in this case, we can define the Stieltjes transform. So as before, some weight over point minus z. And simply, the thing is that we have an infinite sum, so we need to guarantee some kind of convergence. And here, to get something converging, we symmetrize. So we cut symmetrically between minus m, and then we take a limit when m goes to infinity. And we can consider this function. Now what I look is, okay, the Stieltjes transform is defined outside the real line, but in fact, it's also defined. It's in this example, in fact, it's defined everywhere except at the points lambda. So it's and on the real line, so it's differentiable, strictly increasing on each interval of the form lambda L, lambda k plus 1. So here it's, okay, if I have the points here, the Stieltjes transform does something like that. Okay, so it's elementary to check that. And then what happens is if I take a level line, so for example, the line where, okay, let's take level line here, H, then I get a new set of points. And this set interlaces with respect to the points lambda. So this defines a new point process in this way. If we have a point process lambda k, then we get new points interlacing by taking this level lines. Moreover, this new set satisfies the assumptions we used for lambda. Okay, because interlacing means that in intervals we have a difference of at most 1 point, more or less. So the asymptotics are the same. So it means that we can restart with these new points, and we can do again a Stieltjes transform if we like. So we can iterate, and we can also randomize. So how do we randomize? So in fact, we define a Markov chain of point processes. So we start with a random set of points, almost surely satisfying the assumptions I gave before. And then we consider a family of random level and random weights. So family of real numbers independent of the point process. And we suppose that the distribution is invariant by the shift of the index, because there is always a question when we have a set of points. There is a question of numbering the points. And in order to make this numbering not problematic, we assume that the weights, if we shift the numbering, the law of the weights does not change. And then we define a random measure in this way. So we put the points we started with the weights. And then so we have a new measure, and then we can define the still-just transform of this measure. And we choose a level 9. So with the level H0. And then we get a new random set of points. Okay, and then this is this question of numbering, and then we can continue. We can start with L1 and then put fresh weights, compute still-just transform, and take the level lines, and then iterate again and again. And in this way, we construct a Markov chain. But the the Markov chain, so we have a point process, a random set of points, and then we move to another random set of points, and then we move to another random set of points. And then when we iterate, we do it like a Markov chain. So the possible states are the different configurations of points. Okay, and this is what I said, the state space. This is the discrete subset of R satisfying the assumptions made on L before. And if the law is invariant for this Markov chain, which means that the distribution of this point process is the same as the distribution of this point process, then we can couple the Markov chain and get something stationary. So we would get a stationary Markov chain, and we can start from -infinity, because we can start from the invariant measure, and then when we couple, we can define something starting from -infinity, and then we deduce a random point process on Z times R, because we can start from -infinity, and then if we have a -1, 0, 1, 2, and we start with some levels, and we do this Markov mechanism. So S -1 of some measure. Then we do again and again, and everything is compatible. So we define it this way, a point process on Z times R. So now I will give an example, and this is what will give the bead process for beta ensembles. This will be precisely an example of construction where this construction mentioned here works. So I recall what is a Gaussian beta ensemble of dimension n, an exponent. So there is an exponent beta, the parameter beta. So it's a random set of points on the real line with density given by or proportional to this. So we have product of the distances between points to the beta times some Gaussian density. And for beta equals 1 to 4, this corresponds to the eigenvalue distribution of the Gaussian orthogonal ensemble, the Gaussian unitary ensemble, and the Gaussian symplectic ensemble, respectively. So it has been proven by Valco and by Lint that a suitable normalization of the Gaussian beta ensemble at the microscopic scale converges in law to a limiting point process called sin beta. If we look at the eigenvalue at the points of the G beta E, Gaussian beta ensemble, and zoom around some point in the bulk, then we get at the limit this sin beta point process. There is also something, so for the circular beta ensemble, so there is a result by Kilip and Stoiciu, also giving a convergence, for a circular ensemble to this sin beta point process. And for beta equals 2, the sin beta process is the determinantal sin kernel process, coming from the Gaussian unitary ensemble. So this is the sin kernel point process corresponding to one line of the bead process by Boutillier, if we compare with the beginning of the talk. So in our joint paper with Malint, we prove that the law of the sin beta process is invariant for the Markov chain if we take a particular level h and particular weight. So we have to choose the weight suitably. Under this distribution, so the level h is deterministic, and the weights gamma are IID gamma distributed with parameter beta over 2 in order to have an expectation equal to 2. So with a normalization of the weights. And for beta equals 2, in fact, the point process associated to this Markov chain has the same law as the bead process introduced by Boutillier for a certain parameter gamma function of h. So it means that our construction generalizes the bead process to general values of beta. Okay, so now so we have seen that the bead process is the limit of the eigenvalues of the minors of GUE at successive levels. And in fact, this can be generalized to general beta by introducing something called the Hermite beta corner. So this is introduced by Gorin and Skolnikov. So it's a particular family of point processes with interlacing. So we have, so we go up to n, and then so we have a triangle of points like this, which interlace. Okay, so it's a configuration of points like this. So it's a finite version of the bead process somehow. And there is a joint density explicitly given, such that here you have G beta E, here 5, and then G beta E 4, and so on. So each line corresponds to the G beta E, and between different lines, we get interlacing points. So moreover, for beta equals 1, beta equals 2, beta equals 4, the points here are distributed like the eigenvalues of the successive top left minors of the Gaussian orthogonal ensemble, Gaussian unitary ensemble, and Gaussian symplectic ensemble, respectively. So we have this GUE matrix, and then we take the minors here, and we look at the eigenvalues, and the distribution, the joint distribution of all eigenvalues of all minors corresponds to what is introduced by Gorin and Skolnikov for beta equals 2 for the GUE, and for GOE, it's 1 and 4 for GSE. And what is called, so these random points are called Hermite beta corner. So it can be somehow seen as the set of eigenvalues of minor of the Gaussian beta ensemble. Of course, this is only informal because we don't have matrices involved when we construct the G beta E. So we can, talking about minors of matrices, it's somehow not really accurate, but.
What happens if you take the tridiagonal model?
So yeah, there is a tridiagonal model with. Yeah, so if we do that, we don't get the same. I think for two levels, two consecutive levels, we get the same. If we take the tridiagonal matrix and then the principal minor, in this case, the joint distribution of the two lines of the eigenvalues is the same as this one, but it's only for two. Oh, if we take more than two levels, it's not the same. Yeah.
Oh, I see.
And the Hermite beta corner, in fact, can be constructed differently. So the construction by Gorin and Skolnikov is by taking a density, a joint density of all the sets of points. So there is an explicit formula. And in fact, there is another way to construct the process. So we start with a centered Gaussian variable. And then we do also a Stieltjes transform, modified Stieltjes transform, and take, so we introduce, so at each step, we introduce a new Gaussian variable, and we introduce some weights, gamma distributed, and okay, so we have the different normalizations, and we take the zeros of some function, which is given here. So the equation above is related to the previous construction of Markov chains. But of course, here it is finite. So it's different, but it's somehow the same principle. So we can imagine that we can get a scaling limit. So what do? We fix a parameter. It corresponds to a point in the bulk of the spectrum of the Gaussian beta ensemble and some integer. And then we define the set. So we extract from the beta Hermite corner, we extract a certain number of consecutive levels. So here we go from levels n minus capital K to n plus capital K, and K is fixed. And we want n goes to infinity. So we extract a finite number of levels, and then we transform them. So we subtract alpha square root of n, and then we rescale. And we do that. And if we do that, so in our paper, we prove that we have a convergence of the, so of these level, these extractions, so this extraction of Hermite corner. So after normalization, they converge to the bit process, the beta bit process we have constructed in our paper. Okay, and then we have explicit expressions for the level and the weights. So more informally, we have proven that the beta Hermite beta corner converges in the microscopic scale to our generalization of the bit process for beta ensembles. And this is basically how we prove that for beta equals 2, the beta bead corresponds to the bead process of Boutillier, because we know that the Hermite corner converge to the beta bead. And then for beta equals 2, it corresponds to the minors of the GUE converging to the beta bead for beta equals 2. But it's already known that it converges to the bead introduced by Boutillier. So by comparing the two results, we deduce that the bead by Boutillier is recovered by our construction for beta equals 2. Okay, so this is what I said. Okay, and beta equals 1, beta equals 4. So we deduce the convergence of the suitably renormalized eigenvalues of the minors of the GOE and the GSE. Okay, so thank you for your attention.